Okay, we're still on this unit about polynomials, and today we're going to be talking about roots and zeros. Now, we've talked about roots and zeros in the past, okay? In fact, we talked about roots, zeros, x-intercepts, solutions. Those sometimes are used interchangeably, okay? And basically, it's where the graph crosses the x-axis, except when you have imaginary solutions. If you have imaginary roots or solutions, it's not going to cross the x-axis at that spot because it's imaginary, okay? All right, so basically this concept summary here just says you have a polynomial function. If you have a constant that's a zero of the function, then that constant is a root or solution of that function set equal to 0, okay? Then x minus c is a factor of that polynomial function. And if c is a real number, then c0, that ordered pair, is an x-intercept, okay, if c is a real number. So you can have roots or solutions that don't cross the x-axis because they're not real. They're in the complex system. All right, fundamental theorem of algebra. Every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. Now, you probably remember from quadratics, you can have a quadratic that never crosses the x-axis, right? Okay, but the fundamental theorem of algebra says it's still going to have at least one root. It'll be in the complex number system, but it's still going to have at least one. Okay. Now, example 1, we're going to determine the number and type of roots. So example 1a, we have the polynomial, actually this is quadratic, x squared plus 6x plus 9, and it's set equal to 0. And we want to know the number and type of roots. Well, we're going to need to find the roots so we'll know. So, this is a quadratic. It has no GCF. You can factor it. You could use quadratic formula since it's a quadratic, but we're just going to factor it. Because factoring is, if you can factor it, it's usually quicker and easier than quadratic formula. So we put an x here and an x here, and two numbers that multiply to get 9 and combine to get 6 would be. So we ended up with a repeated factor, x plus 3, x plus 3. So you're going to set it equal to 0. So x would be negative 3. Adele, are you getting this? All right. So x equals negative 3. Now somebody asked last period, well, since there's 2 of them here, do you have to list this twice? No. All right, so the number and type of roots. This one has one real root, and we're going to add the word repeated. Now, you don't necessarily have to put that on your assignment, but this one has a repeated root. This is going to be one of those quadratics, one of those parabolas that just sits on the x-axis, okay? Okay, example 1b. X cubed plus 25x equals 0. Now, this is a cubic, so we can't just stick it in the quadratic formula. It's called a quadratic formula for a reason, okay? So you want to try to factor it if you can. So can we factor this one? What about our GCF? So we need to factor that out first. So what do we have left?
Okay, yeah.
Now, can x squared plus 25 be factored any further? No, it can't. Okay? It's not a difference of cubes. It's a sum, difference of squares. It's a sum of squares. And a sum of squares cannot be factored. Okay? So, but we have it now where we can set each of these equal to 0. Now, so if we set this one equal to 0, then that's our solution, 0. So one of our solutions is 0. Now, if we set x squared plus 25 equal to 0, there's two ways you can do this. You can do quadratic formula, where a is 1, b is 0, c is 25. Or, since there's no middle term, since there's no x term, you can move the constant over here and then just take the square root of both sides. Maybe that's a lot quicker. So, subtract 25 from both sides. So you get x squared equals negative 25. Then to get x, you take the square root of both sides. So x equals plus or minus the square root of negative 25. You have to remember, if you do that method, the square root method, you have to consider the positive and negative roots. Okay, now I have a negative under the square root. What do I do about that? Well, I think I heard somebody say it. I. So we can take the negative 1 out as I. Now, what's the square root of 25? So, x equals plus or minus 5i. So then my roots are 0, 5i, negative 5i. So what kind do I have? Well, what kind of root is 0? Is it real or imaginary? Is 0 a real number? Yes. So we have one real root. And what kind of numbers are 5i and negative 5i? So we have two imaginary roots. Now somebody put this in the calculator, x cubed plus 25x in your graph. Go to graph. Now based on what you see here, while she's doing that, where do you expect this graph to cross the x-axis? Well, they're not all imaginary, though.
Zero.
Okay, so I would expect that this graph is only going to cross at 0. But it still has 3 roots. There's 2 of them are imaginary. Anybody get it?
I'm good on my calculator.
Okay.
What are we doing?
Here it is. We're just graphing it. Here's x cubed plus 25x. Now I would need to zoom out, but you can tell where it crosses. Where does it cross the x-axis? At 0. That's the only place. Is she sick? Mackenzie, are you sick?
No.
Okay, well.
Just say yes. Mackenzie, are you sick?
Okay. Anyway, even zooming out, it's still hard to see. So, but you can see that it crosses at 0. Or not.
That's all it says. It's going to be on video. What'd you say? Yeah.
Okay, we're going to do one more. Example 1C. X to the fourth minus 16 equals 0. We're still doing the same thing. Now this is a fourth degree function. And I see two terms. I don't see a GCF. So anybody have any suggestions? We can factor it. You say difference of squares? Okay. We can factor it because this is a difference of squares. Because x to the fourth is a perfect square. It's x squared squared. Minus 16 equals 0. So I can do the difference of squares. Take the square root of each each term, put a plus in between them and a minus. So the square root of x to the fourth is x squared, and the square root of 16 is 4. So x squared plus 4, x squared minus 4. But our two factors are quadratic now. They're not linear. If they were linear, we know we'd be done. But if they're quadratic, you need to check and see if it can be factored more. Can it? All right, this one right here is a difference of squares. This one is not. It cannot be factored any further. So you should bring it down. But this one is another difference of squares again. So take the square root of each, which is x and 2. So we have x plus 2, x minus 2. So now we're ready to set them equal to 0. So let's start with x squared plus 4. X squared plus 4 equals 0. Subtract 4 from both sides. X squared equals negative 4. You take the square root. So x equals plus or minus the square root of negative 4. So what do? I'll take care of that negative first. So x equals plus or minus I times the square root of 4, positive 4, because the negative, we took it out. That's what I call it. And then what's the square root of 4? So x equals positive or negative 2i. Now we need to set x plus 2 and x minus 2 equal to 0. So x plus 2 equals 0, so x would be negative 2. X minus 2 equals 0, so x would be positive 2. So my solutions are negative 2, 2, negative 2i, and 2i. Doesn't matter what order you put them in. So now we got to tell how many and what kind of each. Or find what kind and then tell how many of that kind. So do we have any real solutions? Negative 2 and 2 are real, aren't they? All right, so we have 2 real. And then what about negative 2i and positive 2i? That's R-E-A-L. It looks like R-E-A-L. They're what? Imaginary. Okay, now there's a corollary to the fundamental theorem of algebra. And a corollary basically is just kind of an add-on to it or further explain it. Okay, so the fundamental theorem of algebra said that every polynomial equation that has an exponent of 1 or greater, degree of 1 or greater, is going to have at least one root in the complex number system. But the corollary goes on to say not only is it going to have at least one, you can know how many. Because the number of roots is going to match the degree of the function. So here we have a 3rd degree function, so there's 3 roots. Here we have a 4th degree function, so there's 4 roots. 5th degree function, 5 roots, and so on. So the corollary helps us know how many roots we're looking for. Okay? And they can be a mixture of real and imaginary. Okay. Now, there's this mathematician named Descartes, and he came up with this way. Well, before we talk about his rule of signs, let's say that we're looking at this equation right here, or this function, a 6th-degree function. And let's say we set it equal to 0 and we're trying to solve it. And there's no GCF. Let's say we tried grouping. That didn't help. So what else? Do you remember last week when we learned synthetic division? Or how to use synthetic division? So, but we were given a factor, weren't we? Yes. Well, we're not given anything here. So remember, if a number is a root of a polynomial equation, you'll get a remainder of 0 when you do synthetic division, right? Okay. So we could do that. We could do synthetic division to see if we get a remainder of 0. Our problem is what number do we start with? We don't know, okay? Because it could be, our zeros could be any number. So Descartes came up with this rule of signs. And his rule of signs will help narrow it down. So the rule of signs is not, it's a means to an end, okay? It's a strategy to help you get roots, to find roots. So the number of positive real zeros of the function is the same as the number of sign changes. We'll talk about that in a minute, or less than that by an even number. The number of negative real zeros of a function is the same as the number of sign changes in p of negative x, or less than that by an even number. I know that makes perfect sense, right? You understand all that. And don't worry about this over here right now. But basically what it's saying is we can figure out, narrow down kind of, and sort of have an idea of how many positive real zeros we're going to have and how many negative real zeros we're going to have. Now it's going to narrow it down somewhat, but not a lot more than just picking any number out of the sky. So let me show you what I'm talking about. You want to take the function just as it is, and you want to count the sign changes. Okay, so that means start in front of the first term. X to the 6th is positive, right? So if you need to put a little plus right there, you can. So we're going from a positive to a positive. Is that a sign change? Did it change? No. Okay, then go from this one to this one. We go from a positive to a negative. Is that a sign change? Yes. Then negative to negative. No. Negative to positive. Yes. Positive to negative. Yes. Negative to positive. So Descartes' rule of signs says that we got 4 yeses, so 4 sign changes. So that means there's going to be 4, 2, or 0 real positive roots. And that's what it means by less than this by an even number. So we got 4 signs, so less than that by an even number. So in other words, just subtract 0. Subtract 2. Until you get to 0.
So that's the answer, 4, 2, 0.
Well, that's how many real positives are going to be. We know that there's going to, there could be 4, there could be 2, or there might not be any.
I'm saying we're working in any part.
We got to do the negatives now. Okay? So, we got to do positive, negative, and imaginary. So now let's do negative. Descartes' rule of signs says, find p of negative x and count the sign changes. Now, I'm going to do this the long way first and then show you the shortcut. And some of you may pick up on the shortcut as we're doing it. So basically what I want to do is I want to replace all my x's with negative x's and then raise them to each power. So we'd have negative x raised to the 6th power plus 3 times negative x raised to the 5th power minus 4 times negative x raised to the 4th power minus 6 times negative x raised to the 3rd power plus negative x squared minus 8 times negative x plus 5. So what would negative x to the 6th be? Negative x times 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 negative x. Would it be positive or negative? Positive, right. Because when you multiply two negatives, it's a positive. So 2 would be positive and 2 more would be positive. 2 more, you see what I'm saying? So if the exponent's even, then it's going to be, okay, so you're figuring out the shortcut. So this would still be x to the 6th. It's still positive, just like it was up here. Now what about negative x to the 5th? What would that be? It'd be negative. And so 3 times a negative x to the 5th would be negative 3x to the 5th. Okay, what about negative x to the 4th? It would be a positive x to the 4th, so that sign does not change. What about negative x cubed? Negative, so you'd have a negative times a negative, which would be a positive 6x cubed. Okay, what about negative x squared? That would be a positive x squared. So that sign doesn't change. Okay, then we have negative 8 times negative x. That would be that would change to positive, right? And then the 5 stays the same. It doesn't have an x with it, so it's not going to change. So the shortcut, instead of doing all this, what you can do is look at your original. Change the signs only of the ones who have an odd exponent. So notice, x to the 6th stayed x to the 6th. Negative x to the 4th stayed negative x to the 4th. It's an even exponent. X squared stayed x squared, positive x squared. But then look at your odd exponents. 3x to the 5th is negative 3x to the 5th. Negative 6x cubed became positive 6x cubed, and negative 8x became positive 8x. Okay? So that's your shortcut. Just go through and change the signs of the ones with odd exponents. So let's count our sign changes now. Positive to negative. Yes. Negative to negative. No. Negative to positive. Yes. Positive to positive. No. Positive to positive. No. Positive to positive. No. So how many negative reals are we going to have? 2 or 0. You've always got to subtract 2 each time. R-E-A-L. There. All right. So we're going to have 4, 2, or 0 real positive, 2 or 0 real negative. Now we got to figure out how many imaginary. Okay? So I'm fixing to make a table, but I'm going to have to write really small. Wish I had just a little bit more room. So you find your imaginary based off of what you got here. Okay, so let's do a little table. We have our number of positive, the number of negative, the number of imaginary, and the total. Now our total, since this is a 6th degree function, we know we should have 6 total roots. So now we got to take all of our possible combinations based on what we've got up here. So let's say we had 4 positives, 2 negatives. How many is that altogether? 6. So how many imaginary could you have in that scenario? None, because it can't be more than 6. All right, well, let's say we had 4 positive and 0 negative. How many imaginary would we need to have a total of 6? 2. All right, let's say we had 2 positive and 2 negative. Then how many imaginary would we have to have? 2. Let's say we had 2 positive and 0 negative. How many imaginary would we have to equal 6? 4. All right, let's say we have 0. Yeah, no, there's 2 more. Let's say I have 0 positive and 2 negative. Then how many imaginary would I need to equal 6? 4. This is the last one. If I have 0 positive and 0 imaginary, 0 negative, how many imaginary would I need? I'd need 6. So look at this column right here. How many imaginary are there going to be? So 6, 4, 2, or 0 imaginary. So those are your answers to that question. Now the purpose of that, we're going to stop right there because that's all they ask us to do in this problem. But the reason you do this is now you can take it a step further and you kind of know when you start trying numbers to see if they're roots, you'd at least kind of know how many you're looking for. So let's say, for instance, you got 0 sign changes here and it was just 0 negatives. Well, then you would want to try -1 and -2 and -3. You see what I'm saying? So it's a strategy to kind of help you. And there's another strategy that we're going to talk about later that'll help narrow it down even more. Okay? Now, tomorrow, we're going to stop right there because that's where I stopped with the other class. But tomorrow, now, why does it do that? The camera, if there's just a little bit written on the page, it won't focus. It's still not focusing. That is weird. Even with that up there now, it will not. There it goes. Once I have some writing up there, but watch when I pull this down. Okay, it stayed. Okay, so tomorrow we are going to now put everything together. We're going to use synthetic substitution and we're going to use Descartes' rule of signs to figure out what numbers we need to start with. So aren't y'all excited about that?
Yes, that's tomorrow. So,